Hello everyone, welcome to my presentation. My name is Xi. I'm from the Institute of ISM in TU Darmstadt, Germany. It's my pleasure to present our work on behalf of all the courses. The title of our paper is Internal Flame Structures of Thermo-Diffusive Lean Premixed Hydrogen Air Flames with Increasing Turbulence. Hydrogen is widely considered as a promising carbon-free fuel that can be used in the future internal combustion engines and gas turbines. However, lean premixed hydrogen air flames feature thermo-diffusive instabilities as they have Lewis numbers much lower than unity. In laminar flows, cellular burning patterns have been observed in our previous studies with lean premixed hydrogen methane air polyhedral flames. In turbulent flows, turbulence flame interactions enhance thermo-diffusive instabilities at low to moderate turbulence levels, resulting in a locally intense burning, whereas high turbulence suppresses the thermo-diffusive instabilities, resulting in a more homogeneous burning. The objective of this study is to investigate the transition of the turbulence chemistry interactions in lean premixed hydrogen air flames with increasing turbulence level. My talk will be in the following three parts. First of all, I would like to introduce the experimental setup used in this study, which include the piloted turbulent jet burner, simultaneous OH leaf and PIV measurements, as well as quasi-simultaneous 1D Raman-Rayleigh and 2D Rayleigh scattering measurements. Then, I will present the main results and discussion, including the turbulent flow fields, instantaneous flame structures, and thermochemical states of the measured flame. Finally, I would like to end the talk with the conclusion. A schematic figure of the piloted turbulent jet burner is shown on the left side. The burner consists of an outer porous cold flow ring, a middle porous pilot burner plate, and a centered jet nozzle with an inner diameter of 4.5 mm. In this study, 4 premixed hydrogen air jet flames with a global equivalence ratio of 0.4 and different jet velocities varying from 50 to 200 meters per second were studied. The long exposure chemiluminescence images of the flames are shown on the right side. A primary difference between the current study and the previous investigation is that both the pilot and the jet were operated with the same fuel-air mixture to avoid producing a stratified flame. Laser-induced fluorescence of OH radicals was used to visualize the macroscopic flame structures. The experimental setup is highlighted on the right side. A dye laser was pumped by a frequency-doubled anti-arc laser to generate excitation beam with a wavelength of 283 nanometer. The leaf signals of the OH radicals were imaged by a CCD camera equipped with an intensifier, a UV lens, and a bandpass filter. The spatial resolution is 23 micrometer per pixel. Simultaneously, particle image velocimetry was used to measure the turbulent flow fields of the flames. The experimental setup is highlighted on the right side. A double cavity frequency double anti-arc laser was used to provide double pulses with a delay time of 1 microsecond. Aluminium oxide was used as tracer particles in the jet flow. The mist scattering from the tracer particles was recorded using a S-CMOS camera equipped with a macro lens and a bandpass filter. The spatial resolution is 16 micrometer per pixel. Spontaneous 1D Raman-Rayleigh scattering was used to measure the temperature and the number density of major species in the flames. The principles of the Raman-Rayleigh scattering are shown on the right side. A molecular is excited by a laser photon into a virtual state. If the molecular falls back to the ground state, it will emit scattered light with the same frequency as the incident light. This is Rayleigh scattering. If the molecular falls back to an excited state instead of the ground state, the scattered light will have a different frequency and energy compared to the incident light. This is Stokes Raman scattering. Theoretically, the Rayleigh temperature is inversely proportional to the Rayleigh signal, and the species number density is proportional to the Raman signal. The experimental setup of the 1D Raman-Rayleigh scattering system is shown in this slide. The excitation lasers are shown on the left side, which include 4-frequency double anti-arc lasers operating at 5 Hz. 3 optical delay lines were used to stretch the laser pulse to avoid optical breakdown. The combined laser beam was then focused into the pulse volume with a waist diameter of 190 micrometer and a total energy of 1.8 joule per pulse. The spectrometer is shown on the right side. The signal within the 6 mm pulse volume was collected into the spectrometer through an achromatic lens, and its optical resolution is about 60 micrometer. A rotating shutter system was used to reduce the background signal, resulting in a gating time of 361 and 3.4 microseconds for Rayleigh and the Raman camera, respectively. The Rayleigh signal with a wavelength of 532 nanometer was captured by the Rayleigh camera with a spatial resolution of 20 micrometer per pixel, and the Raman signals of major species with wavelengths between 550 and 700 nanometer were collected by the Raman camera with a spatial resolution of 50 micrometer per pixel. A 2D Rayleigh scattering measurement was performed quasi-simultaneously with the 1D Raman-Rayleigh measurement to visualize the flame. A frequency triple anti-arc laser with a wavelength of 355 nanometer was used as an excitation laser to avoid signal overlay with the 1D measurement. The incident laser sheet was inclined by 8 degrees to avoid optical overlay with the 1D system. A schematic figure is shown here to illustrate the relationship between the 1D and the 2D lasers. The 2D Rayleigh scattered light was collected by a CMOS camera coupled with an intensifier, a UV lens, and a bandpass filter. The spatial resolution is 20 micrometer per pixel. Next, let's move on to the result and discussion. In this work, calories number was used to quantify the turbulence level in the measured flame, and it can be calculated by equation 1, in which U prime is the turbulent velocity, L is the integral length scale, SL is the laminar flame speed, and LF is the thermal flame thickness. The mean axial velocity U and the turbulent velocity U prime derived from the PIV results are shown in the middle. The integral length scale was estimated by the half width at half maximum of the mean axial velocity profile, according to previous study, to give an estimated calories number range. The turbulent velocity at the jet center, denoted by U prime C, and the maximum turbulent velocity in the flame, denoted by U prime F, are used to calculate the calories numbers. As shown in the table, the maximum calories number for the measured flame with increasing jet velocities varies from 50 to 730. Based on the derived maximum turbulent velocity and the integral length scale, the combustion regimes of the measured flames are identified in the Bogie-Peters region diagram on the right side. As can be seen from the figure, the combustion regime moves from the thin reaction zone to the distributed burning regime with the increase of the jet velocity. To the best of our knowledge, the current work presents the first experimental result on lean premixed hydrogen air flames in distributed burning regime. The instantaneous flame structures visualized by the single-shot OH leaf images are shown in this slide. The color bar indicates the OH signal intensity. The flame surface was detected by the maximum OH signal gradient, and the flame surface curvature was derived from the intensity gradient map. As indicated by the second color bar, the concave flame surface toward burn site has a positive curvature. At low turbulence level, as shown on the left side, cellular burning patterns with large cell structures are observed, and burning regions with positive curvatures are prone to have a higher OH intensity. As calories number increases, the flame surface is more disturbed by the turbulence. At high turbulence level, as shown on the right side, the flame surface is more wrinkled with smaller cell structures, and the burning becomes more homogeneous. To quantify the internal flame structures of the intense burning regions observed on the OH leaf images, single-shot Raman Rayleigh results with low turbulence levels are shown in this slide. On the left-hand side, the flame structure is visualized by the inversed 2D Rayleigh signal, in which the green line indicates the 1D pulp volume. The corresponding hydrogen mole fraction and water mole fraction are shown on the second row, in which the green dashed line indicates the hydrogen mole fraction in the reactants, and the blue dashed line indicates the water mole fraction in the products. The local temperature and equivalence ratio are shown on the third row, in which the black dashed line indicates the adiabatic flame temperature, and the red dashed line indicates the global equivalence ratio. Intense burning is observed in the post-flame region with positive curvature. In this region, the highly diffusive hydrogen is focused toward the burn site, resulting in a locally fuel-enriched burning with a higher equivalence ratio, higher water mole fraction, and superadiabatic flame temperature. The figure in the middle shows the corresponding result in the temperature domain. The color bar denotes the spatial position. To demonstrate the differential diffusion effect, 1D simulation results with multi-component transport, shown as blue lines, and unity Lewis number, shown as red lines, are included for reference. The flame can be roughly classified into three regions, as indicated by the dashed line in the spatial domain. In the inner region, the profiles follow the multi-component simulation curves and extended to superadiabatic flame temperature. In the middle region, the paths are parallel to the multi-component simulation curves, but with an overall higher equivalence ratio. In the outer region, the data points are mainly from the pilot flame. Furthermore, the single-shot Raman-Rayleigh results with increasing turbulence level are shown in this slide. As can be seen from the figure, the cell structure becomes smaller and the local intense burning near positive curvature is weakened as turbulence level increases. At high turbulence level, as shown on the right side, no superadiabatic flame temperature is observed in the corresponding regions, even though a locally high equivalence ratio is built up. To further quantify the thermochemical states, the conditional mean and fluctuation of hydrogen mole fraction, water mole fraction, and equivalence ratio over temperature are shown in this slide. Again, the 1D simulation results with multi-component transport and unity Lewis number are shown as blue and red lines. At low turbulence level, the measured mean profile are similar to the multi-component simulation curves with a bold distribution. Elevated water mole fraction and equivalence ratio with superadiabatic flame temperature are clearly observed, which indicates that the molecular diffusion still plays a significant role in the mixing process. With increasing turbulence level, the conditional mean profiles move closer to the unity Lewis number simulation curves with a smaller fluctuation. At high turbulence level, the hydrogen mole fraction has a more linear decreasing trend, and the equivalence ratio is flattened to a constant value with a narrow distribution. This indicates that the turbulent mixing dominates over the molecular diffusion in the mixing process. Finally, we come to the conclusion. A clear transition from diffusion-dominated mixing to turbulence-dominated mixing is observed in lean premixed hydrogen air flames with increasing turbulence levels. Specifically, at low turbulence level, locally intense burning characterized by an elevated water mole fraction and equivalence ratio with superadiabatic flame temperature is observed in regions with positive curvature. At high turbulence level, homogeneous burning is observed in which hydrogen mole fraction has a linear decreasing trend and the equivalence ratio is flattened to a constant value in the temperature domain. This work is funded by the German Research Foundation, and I would like to take this opportunity to thank all the co-authors in this work. Finally, thanks for your attention.